inviting me to give a talk here. So I'm Patrick Farrell, and I don't do any atomistic simulations. I remember the confession. I'm a numerical analyst, and I work mainly in the numerical approximation of solutions of nonlinear partial differential equations. And in that context, I became very interested in nonlinear PDEs that supported multiple solutions. And for maybe 10 years or so, I've worked on a numerical technique for calculating multiple solutions of nonlinear problems. For me, they're PDEs, but the technique is more general. And that's what I hope to present today. Okay, so maybe let me start with some philosophy. Maybe this won't be too surprising to this audience, but to other audiences, it is surprising that you can ask a seemingly well-posed question, like if I apply a given load to a particular structure, can you get multiple answers for the same question, right? And the answer is yes, right? And to me, I don't think the philosophers of the scientific method or scientific reproducibility have necessarily engaged with this question as much as perhaps they should have done, because if a problem has multiple solutions, then it may be the case that failure to replicate does not mean invalidation of a theory. So here's an example that arose in my consultancy, actually. I was in Brazil. I was at the Embraer factory, the world's third biggest manufacturer of airplanes. And they came to me with these aircraft stiffeners. So they're about 5 centimeters long. They're made of aluminium. They provide rigidity to the hull of an aircraft. And in order to certify their planes to be flight worthy, they have to characterize at what loads these fail. But with this particular design that they had found that, in fact, when they did the samples, when they really did the physical experiments, not just numerical experiments, that they were observing two different failure modes, one where this flange buckles out and one where this flange buckles in. And then as they kept loading them, there were more and more different kinds of solutions that were arising. And in order to guarantee the flight worthiness, they had to say over all possible paths that this experiment might take, all different configurations that it might adopt, that it won't fail above a certain load, right? So they needed to calculate all of the solutions of this problem. Okay, another example from aeronautics is in fluid mechanics rather than structural mechanics. So this story amuses me greatly because I really love the idea of sort of a group of people like us here being really confused. So this is the trapezoidal wing. And the aeronautical engineers have a wonderful tradition of challenging each other. Okay, so what they will do is someone will go and put this wing, of course it's on its side, right? So the wing is this way, in a wind tunnel. This is the wind tunnel at NASA Ames, and they'll do the experiments, right? So they'll see for a given, inflow wind condition, what is the lift and drag and what does the flow look like? And then they'll specify everything that you need to know to simulate the system, like the geometry and the inflow and and so on. And then they tell people, please go away and simulate it. And then they meet in 6 months or a year, and then they see whose code got it right, whose code got it wrong. Because at the end of the day, if you're going to design aircraft with computational models, then people's lives depend on this. And what happened when they all met up to compare the results of their model was that the groups divided into two, where some people had a solution that looked something like this, and the other half had solutions that looked something like this. And of course, they both thought that the other one was wrong. And so there were various arguments about whose codes were better, and your discretization is terrible, and you're not very good scientists, and so on. But it turned out that actually this is just a nonlinear problem that has multiple solutions, and they were both right. And eventually it was resolved by these guys at Boeing. This paper is from authors at Boeing, where they had two codes that had yielded the two different solutions. But then if they used this solution B, as initial guess in solver A, they could recover solution B, and vice versa, right? And it turned out that this was a hysteresis loop, that somehow if you ramp up the angle of attack from the state where the flow is attached, it remains attached. If you start from a very high angle of attack where the flow is separated, and you bring it down to this configuration, the flow remains separated. So there were two stable equilibria. So what does this mean for us? Well, what does it mean? Okay, so there's a PDE. It has two solutions, and I'll always draw my solutions with these stars. And then I'll start from some initial guess, and I'll drive my nonlinear solver, for me always Newton's method, but I think in your context usually not Newton's method, to my solution, which is I publish this as my prediction, right? And if I'm really careful, if I'm really sophisticated, I can have a posteriori error estimates, and I can certify that I've got the thing I'm calculating to within 0.01%, And this is brilliant, right? Except nature chooses the other solution, and my calculations, although they were completely correct, are wrong. They give the wrong prediction because they were incomplete. And so if you don't find multiple solutions when they are there, it means that all of your calculations can be correct, but you didn't do enough of them. You didn't find the solution that nature will see. Okay, so what am I doing mathematically? I'm trying to find multiple solutions, U star, of some nonlinear equation that depends on a parameter. Okay, so U star is the solution for me of a PDE, lambda is my parameter. Okay, and I'm going to assume that this residual, the thing I'm looking for the roots of, is sufficiently differentiable at C1, and it takes in a function in a function space. So here x is a Banach space, but just think of it as real numbers, Rn if you want, and y is another Banach space, Rn, if you want to keep it simple. Okay, and so for the two examples that I've specified, U is a vector field describing the displacement of a structure, lambda is the loading, how much load I've imposed on this aircraft stiffener, and F is the derivative of the hyperelastic energy functional. So this is a case where the equations are symmetric, there is an underlying energy. The second case, U star is the velocity and the pressure, or maybe also temperature if you're compressible. Lambda would be the angle of attack, and F would be some flavor of the Navier-Stokes equations. Here is a case where there is no underlying energy and the equations aren't symmetric. And so I think another place where these ideas would have to be adapted to your context is that, as I understand it, you always have energies, right? And so this is a really special situation that you want to exploit if you can. I wanted to keep it general because I'm interested in problems that are not series. Okay, and a confession at the start that I usually cannot guarantee that I will find all solutions, right? So this is a really important disclaimer. I don't claim to have a magical machine that can find all solutions of a nonlinear problem. Essentially because, well, somehow there's a conservation of misery principle in the universe, right? You can take almost any famous mathematical problem and you can write it, if you wanted to, as a nonlinear equation. And then if you could find all solutions of the nonlinear equation, you could prove Goldbach's conjecture or the Riemann hypothesis or what have you. And then I would be off collecting my Fields medal, right? So the universe won't be so kind as to let us do that. But in some cases, we can guarantee that we can find all solutions, but you have to be problem specific. But even if you can't, I would still say that finding many is better than finding just one, right? Okay, so let me briefly review the classical techniques that Maciek mentioned. Here's my presentation of it. Okay, and so I would say that these ideas go back to a guy called Herb Keller in the 70s that really pioneered this business of numerical bifurcation analysis, numerical continuation. And so here's how I think, here's his schema of how the world should work. So you start off with an initial solution for an initial parameter of your problem. Okay, and I already know one solution of this. And maybe I can choose an initial parameter so that this is trivial, right? If I impose no load on a structure, there is no displacement. That's easy. Okay, so then I'm going to continue branches of solutions. So this is using the implicit function theorem to extend our knowledge of a branch of solutions to other values of the parameter. Then as I travel along this continuation process, I'm trying to detect bifurcations where something interesting happens. So I need to detect somehow how a bifurcation occurs, and I'll talk a little bit about that. And then once I know that something has happened, but I don't necessarily know where, I just know between here and there, something interesting happens, so I need to find out where it happened. I need to localize. And then once I have localized, then turns out I need to go back, I can switch branches. Okay, so I can go to the bifurcation point and jump onto another branch that emanates from that bifurcation point. Okay, and then once I have all of these algorithms, all of these tools in place, I can apply it recursively. So I can start at one point, trace out the branch, and then trace out all daughter branches, and trace out all daughter branches, and trace out all daughter branches until the cows come home. Okay, so here's a cartoon of this process. So we draw our bifurcation diagrams typically with the parameter on the x-axis and the solution or some functional of the solution on the y-axis, right? And this is just a cubic polynomial, so it really is the solution, but of course in general this is some function and I have to energy or some functional of it. And what does this say? It says that up to here, there's only one solution of the problem, but then there's a bifurcation, and it goes from having one solution to having three solutions. Okay, so let's see how Keller's procedure works. So we do continuation. So somehow we use knowledge of this solution to get knowledge of a solution here at this updated parameter value. We can do the same, but now if we just did continuation, we would neglect the fact that there were these emanating branches that came out. So I need to do something extra. So I need to detect that somehow the bifurcation has occurred. Once I do that, then I can invoke some heavier machinery to try to figure out what is this bifurcation point. Usually you can do that by, well, either bisecting on your detector, or by solving an augmented system of equations that describes what it means to be a bifurcation point. So there's an extra system of equations you can describe this point with. And then once you have that, that gives you the knowledge you need in order to construct guesses that will get you onto the emanating branches. And so you do that, and now you can recurse. So this is the basic strategy of how we detect multiple solutions of a problem. Okay, so it's very, very powerful. There are engineering departments where this is the main workhorse of studies, right? For example, I was in the mechanics laboratory in Paris 6 at one stage, and almost everyone was doing this for some engineering problem or another, right? This is really, really a very common and powerful tool. But there are some downsides also that we should be aware of. So the first is that, well, you have to solve a lot of different problems. There's a lot of different moving parts in this approach. So you work for years maybe to develop a good solver for your equations. So in my context, that usually means Newton's method, and then you have big, sparse linear systems to solve, and then you need to develop very sophisticated multigrid preconditioners for them, right? There's a whole industry. People could spend their whole research careers working on how to solve the derivative of this residual, right, in a particular PDE. But now, once you've done that, I tell you, well, now you need to solve all these other systems also. So this is the one that arises in continuation. Maciek had this up. This is an eigenvalue problem, which you might use to detect bifurcations at scale, right? This is the system of equations that describes what it means to be a bifurcation point, this more Spence system of equations. And it turns out that you cannot automatically leverage a good solver for this problem into good solvers for this problem or this problem or this problem. You have to do it in a problem-specific way. Right? Now, of course, if your problem is small, and you're doing Gaussian elimination or direct linear algebra on this anyway, then you can just do direct linear algebra on this, and certainly it helps a great deal with that. But if you really want to do it at scale, where you've got hundreds of millions of degrees of freedom or whatever or more to approximate the solution of your PDE, you really have to think in a problem-specific manner. You cannot just use the solver for this, or this, or this. The other downside, and I would say this is somehow an engineering problem, right? This is just, you have some problems and they're hard to solve, right? They can be hard to solve. But downside B is more conceptual or more fundamental, I would say, which is that the aspiration of this algorithm is to compute those branches that are connected to the data that we supplied, right? That's what it's trying to do. It's not trying to do anything else. So if we apply Keller's approach to this bifurcation diagram, it'll work perfectly, right? This is just a cubic polynomial, a very simple example. But if I perturb the cubic polynomial, so you see I've added a delta up here, and delta is small, what happens is that this pitchfork bifurcation, which somehow is deeply related to the presence of symmetries in this problem. This problem has the symmetry that if u is a solution, so is minus u, right? This problem, because of the perturbation, does not have the property that if you negate the solution, it's also a solution. And that breaks the symmetry, and that breaks this bifurcation diagram apart. And so instead of having a pitchfork bifurcation, you have the kind of fold bifurcations of which we saw many in Fraser's talk earlier. Now, if I apply Keller's framework to this problem, all I will get is this upper branch of solutions. I will never find these disconnected branches down here, because the bifurcation point where the action is happening is over here, right? But I'm not on that branch, so I'll never get there. Okay, and so what do people do? Well, option A is to modify the problem to restore connectedness of the diagram. And then, so you introduce an auxiliary parameter. So I want to solve this problem with delta is 1 over 100, but I'll actually solve the problem where delta is 0, and then I'll take this whole diagram and I'll continue it in another dimension and along the delta axis to get this one, right? That's option A. Okay, but this has big downsides. So first of all, you really have to know that there's something that you're missing, right? You have to know to look for it because this is a lot of work. It's manual and tedious. But more important, I would say, is that restoring connectedness isn't always possible. It's not always as trivial as in this example to just fiddle a parameter and then all of a sudden you restore the symmetry again. You know, maybe the loss of symmetry is because of the domain of the problem that you're solving, and then it's not so straightforward to warp this into a symmetric configuration and then warp it back. Or maybe it's not obvious that there's a symmetry that you've missed, right? Maybe you don't see it. Maybe it's not as straightforward as just as simple as that too. Symmetry. Okay, so the main point of my talk is this business deflation, which we've already heard people don't understand. So it's good that I can try to explain it. And what I would say that deflation is an algorithm for computing disconnected bifurcation diagrams. It's a complementary approach to Keller's very, very powerful and very useful algorithm. And the two big advantages are that it can compute these disconnected diagrams, but it can also, it's very simple if you're doing Newton's method, which maybe isn't so useful for you. Because if you're doing Newton's method, then all you have to do is Newton's method. There are no extra problems to solve, which is very nice for me. Good luck for you. Okay, so let me just briefly, since I'll be talking a bit about Newton's method, let me just briefly remind anyone. I thought maybe there are some people who wouldn't know or wouldn't remember. So Newton's method is the main way of solving nonlinear equations. It has been since, the 1670s or something, right? And maybe it's a little depressing that we still don't understand it. But there you go. Maths is hard. So what is the idea? The idea is the following. I don't know how to solve for the roots of a nonlinear problem, but I do know how to solve for the root of a linear one, right? I do know how to solve for the root of a line. So if I'm at I have some initial guess for my solution, this x naught, and here's my residual, this blue curve, and I'm looking for this point over here. I don't know this yet. Well, I say what I'll do is I'll build the best linear approximation that I can to this function. Here in this 1D case, it's a line. I'll solve for the root of that line. Here it is, right here, and then that becomes my next iteration, right? And then I can do the same. I can build the linear approximation there, next tangent, the root of that gives me the next place to build my tangent, and so on. And already after 3 iterations, we can see that at least to visual accuracy for this sort of somewhat thick black dot, we're already there, and it just gets better and better after that. Okay, and so you can solve explicitly what the root of this linear approximation is if you do a tiny bit of first-year algebra, and what you end up having to do is to solve this linear system in 1D. Of course, this is just a division, but in higher dimensions, this will be a linear system, and then you update your guess. Okay, and so in higher dimensions, here's what it looks like. It took sort of several hundred years to figure out in a rigorous way the extension of this to infinite dimensions. This was one of the great contributions of Kantorovich, one of the great 20th century mathematicians. But here's what it looks like. So you have the Fouché derivative, the Jacobian matrix, if you like, acting on the update. You solve that to be equal minus the residual, and then you do the update. Okay, and the good news is that this converges quadratically if you're close to a solution and it satisfies some mild regularity conditions, which it usually does, right? So this is the main reason why this is the main tool for solving nonlinear problems to this day, because of this exceptionally fast quadratic convergence. All right, so let me now say a little bit about deflation and how this works, the main thrust of the talk. Okay, so what are we going to do? We're going to fix our parameter lambda. So we're just looking at one particular nonlinear problem. We've fixed the parameter dependence. You give me a differentiable residual that goes from my input space to my residual space. So just think of Rn to Rn. That's what you want to do. And then you give me one function that's already a solution, right? So we already know one solution somehow. So it satisfies f of u is equal to 0. And I'll demand some very mild regularity on this solution that the Fauché derivative is invertible or the Jacobian matrix is invertible. You can relax this. It won't change the story substantially. It just makes the exposition a little bit simpler. Okay, and then what we're going to do is construct a new nonlinear problem mapping to and from the same spaces. Actually, it's just going to be a scaling of the original one, in fact. But this G will have the following properties. First of all, it won't lose or gain any other solutions, okay? So if U tilde is a solution of the original problem F, and U tilde is distinct from U, from the one I already know, then that means that it's also a solution of G, if and only if, right? So I can find roots of G, and then that means automatically that there'll be roots of F, and it doesn't lose or gain any solutions as you go back and forth between these problems. And then the second one in words is that if I apply Newton's method to G instead of to F, I will never converge to U again. So I've deflated it away, disappeared, starting from any initial guess, except for U, obviously. Even maybe the initial guess that found us the first solution in the first place. Okay, so it's kind of funny, as a numerical analyst, normally you're trying to guarantee convergence to things. And here I am guaranteeing non-convergence. But non-convergence is something that I already know. Okay, and so if we can do this, then we can find more solutions starting from the same initial guess, right? So this is a way of somehow juicing out more solutions from the same ingredients that you needed to find one. So let's draw a picture. So we've got our Banach space. We've got three solutions of my PDE. I've got my initial guess. I drive Newton's method to convergence. Okay, and I find this first solution. That was what you could do before. And now we deflate it. So somehow it's disappeared from consideration. And now I can start from the same initial guess. And if I converge, I can't guarantee that I'll converge. I'm still solving a nonlinear problem with Newton's method. But if I converge, then I will converge to a distinct solution. Say this U2. And then I can deflate that and repeat the process. Maybe find a third solution, deflate that. And then what? Well, typically, I don't know how many solutions I can expect, right? Sometimes you can put bounds on the number of solutions for very particular problems with very nice structures. We'll see an example of that later. But most of the time I don't know. And so then I have to search. So I do however many Newton iterations you're willing to suffer, 20 Newton iterations, something like that. And then if it hasn't converged, I give up and declare victory. But this doesn't mean that I found all solutions, so there can be other solutions somewhere further away that this process does not find. Okay, so that's very nice if we could do it. How do you actually make this deflation happen? Well, the definition is somewhat tautological, right? So what I'm going to do is I'm going to construct a G by multiplying F with the so-called deflation operator. And what does it mean to be a deflation operator? What it means is that if you take any sequence going towards converging to the solution that we already know, and then I look at the norm of the residual, right? It's bounded away from zero. So Newton is somehow trying to look for sequences where the residual will go to zero. That's what it's for. So if you can make it look like, as you traverse any such sequence, the residual is not in fact zero, Newton, it's greater than zero, so please go away, then Newton will not find the solution again, right? That's the idea. So you just have to guarantee this property of, you have to look at the norm of the residual as you travel along to the solution you already know. And this is what I already said, that the deflation operator hides the existence of such a solution. And once you recognize this, it's very, very simple. Everyone could devise their own deflation operators before they leave this room. There's no one canonical choice, right? But I can tell you my canonical choice, or my choice at least, which is this. So it has two parts, and they're for two different reasons. Here were my co-authors. Okay, and so what are the two parts? So the first part is to make sure that that lim_inf is greater than zero, is to blow up as U approaches U star. And if we blow up at a certain rate P, that has to be greater than or equal to the multiplicity of the root that we have, right? So I always fix P to be 2. I never fiddle with the parameters in this. So this is what's giving me the deflation property. As U approaches U star, on the bottom, this becomes very small. 1 over that is very big. It's to the power P. It's even bigger. And so this is blowing up, right? Faster than the residual is going to 0. So that's why you have this deflation property. The +1 is for the other regime, where u now is very far away from u star. Okay? And so what do I want? Well, really what I want to do is recover the original behavior of the problem. So if u is very far away, then this norm is very large. 1 over that is very small. And so I want this factor to be 1, right? And so I put a +1 there. That's all. Very simple. And so this is the right behavior both as this limit and in this limit. And my main contribution actually to this field, I wasn't the one who invented deflation. It was Brown and Gearhart, building on work by Wilkinson in the 80s, but it didn't really work. And it didn't really work because they didn't have the +1. And so my main innovation was adding the +1. But it turns out that it's a big +1, right? It helps a lot. So it makes it work in a much nicer way. Okay. So once you have this tool, what can you do with it? Well, now let's take a bifurcation diagram that's disconnected, and let's see how we can compute these branches. Keller's approach won't work. So I do continuation. So again, I've used this as initial guess for this nonlinear problem. And in this context, I can actually just even do simple continuation. I don't need to do the arc length stuff. Let's just take simple continuation where I just use this as initial guess for this problem, nothing else. Okay, and then I move on to the next continuation step, and I've used this solution as initial guess for this nonlinear problem, and I found this solution here. But now I deflate this away, and then I look again from this initial guess, and because this point and this point aren't so far apart in function space, I can find this solution also. Then I deflate it away, I look again, I find this solution, my clicker would load, and then I deflate away, I do a search, it goes nowhere because there are no more solutions to find, right? So this process has a lot of waste, but it also has a lot of parallelism. So you can do most of these searches in parallel if you have the resources to hand. It's like one of these cases where, you can just throw a big computer at it. And then when this search fails, we carry on. And now we can go backwards and forwards, and we can fill in the bit that we missed, and we can find the bifurcation points if you wanted to. You don't need to, but you can if you wish. And then you proceed. Okay, so this is what lets us compute these disconnected diagrams. Okay, so there was some discussion of the Jacobian of the deflated problem being dense. And so I just wanted to explain how at least I deal with this problem in the Newton case, where you can solve the problem with Newton's method. It's really no problem at all, but I didn't realize it when I first wrote the papers, which is sort of an embarrassment. I realized it kind of a few weeks after it was accepted or something. Right. Anyway, here's sort of my take on how you should solve these problems now. So in PDEs, we usually have a good linear solver for this discretized Newton step, right? So I've got my Jacobian matrix, I've got the update I'm trying to solve for, I've got minus the residual on the right-hand side. So I just assume I have a good solver for this, and people have shed blood, sweat, and tears in order to make that happen, but they haven't. Okay, and now what I would like to do is to solve the deflated problem. So I've got the deflated Jacobian acting on the deflated update and the deflated residual. Okay, and what is the deflated problem? It's just the concatenation of all of these deflation operators for all of the solutions that I know. And because this is really just a real number, and this is a real number, and this is a real number, I can just gather it as one real number. So I'll call that M. And as Maciek pointed out, this is going to be bad because it's going to make the Jacobian matrix dense, which I thought I had as the next overlay, but it turns out I don't. Because what you've done is you've multiplied every component of F by a number that depends on every component of U. So that's why you get π. But the good news is that we can solve this system mechanically if you can solve this system. There's a way of doing this automatically if you know how to solve this one. And here's how it goes. So this is what Maciek observed, that the deflated Jacobian is what? Well, it's the scaling of the original Jacobian. This I like because this is a number that's not 0, and this is a matrix that I already know how to solve. Right? So I like this term. This is very good. This term I do not like because this is the outer product of two vectors, right? So this is the residual, that's a vector, and this is the derivative of the deflation factor. So the deflation factor is a scalar, its derivative is a vector, and this is a rank 1 outer product, right? So this is this business of multiplying every term by a number that depends on every input. Okay, so I like that, I don't like that. Okay, and so this is dense, right? It's a rank 1 update of a sparse matrix. But once you realize this, you phone your numerical linear algebra friends, and many of you will already know the Sherman, Morris, and Woodbury formula, which, as far as I can work out from the history, there's a nice article in Science Review about the history of this. This formula was by none of these guys, but rather by Bartlett. But anyway, that's how it goes, I'm afraid. So it turns out that if you have a matrix plus a rank 1 update and you look for its inverse, you can write it in terms of the inverse of the original matrix that you know how to solve. Okay, and so here's what it is. A formula that you can check very easily, but is very difficult to come up with a priori, right? But at first, it looks like this will require two solves with the original matrix, right? Because there's an A inverse here, and there's an A inverse U here. But something magical happens, okay? So in our case, in the Newton case. And the reason is that in the Newton case, the vector on the right-hand side of our linear system is the same residual vector as is in the rank 1 update. So something collapses. And what's going to happen is that actually we only need to do one solve with A inverse. So maybe I won't bore you with the algebra, but sort of it's here in the slides in case you should ever need it. And after a lot of tedious algebra, it works out that, in fact, the deflated Newton step is nothing other than a scaling of the original one. Okay, so you can compute your original Newton step, you solve the undeflated problem as you would before, then with one dot product, you compute this scaling, which depends on the solution, right? This is a nonlinear function, but it's just a scalar, just takes one dot product and a few arithmetical operations to compute, although Danny won't like the dot product, right? But anyway, sorry. Okay, and then you just scale it, right? So essentially, this is a few lines of code in between solve the Newton step and do your line search. So that's great. So you can do this at scale. So now we've looked with deflation for problems with hundreds of millions of degrees of freedom or billions of degrees of freedom where you need good preconditions. Okay, so yeah, so this is the recipe, but again, it's just there for reference. So okay, so let's see some examples of it in action for the last few minutes of my talk. All right, so here's just a simple case where, just like the cartoon, I just wanted to show you a real PDE where it happens. This is the Allen-Kahn equation. This is the minimization of an energy, but a non-convex one. And if you impose certain boundary conditions, that it's -1 on the top and bottom and +1 on the left and right, okay, then, and for a certain parameter, this value lambda, and we start from an initial guess of u equals 0, so totally uninformed, it first finds the saddle point, and then you deflate that away, it finds the solution where -1 dominates, you deflate both of those, and then it finds the solution where +1 dominates, right? So this is such a problem with 3 solutions that you just knock out one after the other. Okay, very simple. All right, here's another problem. In this case, just a 1D ODE, but a very interesting and beautiful one. So that this was proposed by a guy called George Carrier in a Science Review paper back in the 70s. And if you ever take it upon yourself to read any books about asymptotics and ODEs, this is a favorite kind of workhorse because it's really amenable to lots of beautiful asymptotic expansions and whatever, right? So if you're into that kind of thing, then maybe you've seen this already. So what is this ODE? So let's see. So we've got a singular perturbation, right? Because our leading derivative is going to 0. Here the regime of difficulty is lambda to 0. We've got a linear term, and we've got a nonlinear term, right? So this is what makes it nonlinear. And we just have 0 boundary conditions, okay? And it turns out that it's not so hard to see that for large values of lambda, this will have 2 solutions, okay? So let's just assume that we know that. And so we start over here. So in this case, we're going this way, right? So we start over here with the 2 solutions that are known at large lambda, and we apply Keller's framework. On one of these branches, nothing happens. On another one of these branches, it has one pitchfork bifurcation. And so it gives birth to 3 daughter solutions, and then nothing happens on those branches after that. Okay, that looks good. But if you look at, for example, the famous textbook of Bender and Ortzag, they have drawings of 8 solutions of this equation, so we're missing something. So at Nick Fethin's suggestion, I applied my algorithm to this problem, and as you decrease in lambda, you find another fragment of solutions, right? So it turns out that there's a disconnected branch of solutions that is born at a fold bifurcation, and then one of the branches undergoes a pitchfork. And then you keep going in lambda, and there's another such structure, and then another such structure, and another such structure, and they're all beautifully nested within each other, sort of like Russian dolls, right? Which is very beautiful. So it turns out that actually this problem has a really beautiful structure that you wouldn't be able to see if it weren't for deflation. Right? If it weren't for deflation, I would have no idea how to acquire this bifurcation diagram. And with this bifurcation diagram, actually, first I computed it, and then my colleague John Chapman managed to prove that, in fact, these are all of the solutions we've captured. All of them, you can put an upper bound on the number of solutions that this problem can have as a function of lambda. Okay, here's another, maybe more recent example, just in the past year or so. I've been working as a consultant for the UK Atomic Energy Authority, which I saw on some people's slides. So this is the Grantchev-Franov equation. So this is sort of like a Poisson, a Laplacian operator, and this is some nonlinear function of the state, okay? And that nonlinear function is usually some polynomial fit to data that they specified. But really, this is the workhorse of fusion experiments because most of the time they don't really have any idea what goes on inside a tokamak. It's extremely difficult to instrument, right? It's like 10 times hotter than the sun. So there's actually very little that you can look into it. So what you do is you take whatever measurements you can, and then you try to fit the solution of this PDE, more or less, which assumes axisymmetric solutions, in order to figure out what the heck just happened in the given experiment that we just did. And so this is solved, many, many times, hundreds, thousands of times per day at the UK Atomic Energy Authority and in other labs as well. And we've recently discovered that it has multiple solutions. And not only that, it has multiple solutions in realistic configurations that are designed to model the UK tokamak as accurately as possible, right? So this is not my code. This was results from people at UKAEA. This is the toroidal slice of mast U, which is the main UK, I think the only UK tokamak. These are the coils that they impose with currents, right? And there's all kinds of specific setups of the PDE to make it like mast U, but there you go. And here we're just showing the separatrix. So the red and the blue are 2 different solutions. I'm sorry that the blue clashes with the blue. I didn't make this figure, but I like it anyway. And for different total plasma currents, this is the parameter that they were varying. It turns out that the tokamak appears to support multiple solutions, right? So for the same coil configurations, the same total plasma current, the same every experimental thing that you can twiddle, there are 2 different equilibria that the tokamak can be in. And this is very interesting because if you know that, then maybe you can try to nudge it to achieve one or the other, right? Or maybe you can even use this in design. And so I think they're very excited about this. I think it has big implications for how they solve the inverse problem. And they've just given me a PhD student to work on things like this. So it's quite nice. Okay, let me also just mention briefly in the last 10 minutes some mathematical extensions of this idea that I think are of relevance to this audience. So the first is this presence of symmetries. Okay, so what if the equation has a symmetry group? Right. So let's be a bit more concrete. That might be a little bit abstract. So imagine you've got a PDE on a disk, and everything about it is rotationally invariant, right? So the forcing and the boundary conditions and all the rest are rotationally invariant. Some solutions will also be rotationally invariant. You rotate them and they look the same. But there might be solutions that are not rotationally invariant. The symmetries of a solution will only be a subgroup of the symmetries of the PDE as a whole. And so if you had a solution that's not rotationally invariant, well, automatically you know that any rotation of it must also be a solution, right? So if you have one such solution, you automatically know a big family of them related by symmetry. And in this case, I would say that the fundamental structure that you're trying to compute are not the solutions, because if you know one such solution, there's an infinite number of related ones. The things that you really want to compute are the families of solutions, which in the lingo of group theory are called orbits of solutions. So it's all the group elements applied to the solution you know. That's an orbit. Okay, and so what we're going to try to do here is to construct a deflation operator that respects these symmetries, that builds in knowledge of the symmetries of the problem, so that we try to attack the orbits rather than the individual solutions. So here's a sketch. Okay, so I've got my Banach space. I've got 4 solutions that aren't symmetries of each other. They're not related by rotation, say. And so what that means is that for each one of them, there's an associated structure. There's an associated orbit in the function space, right? So all the rotations of U1, all the rotations of U4, etc. And if we just did what I did before, where you just deflate an individual solution, that's not enough anymore, because probably what will happen is that if you start from an initial guess here, it'll just go to here, and then it'll go to here, and then it'll go to here, and you'll spend forever just computing different images of the same thing you already know. Instead, you want to deflate the entire orbit, right? So we wanted to build a deflation operator that respects the symmetries of the problem to deflate the entire orbit. And sometimes I know how to do this, and sometimes I don't. So there's sort of an interesting open question at the interface of PDEs and group theory here. Okay, but if I could do such a thing, and sometimes I can, then I can knock out the individual orbits and discover it orbit by orbit. Okay, so here's an example of where I can do it. So this is the Gross-Pilaevsky equation. It's a nonlinear Schrödinger equation that describes an exotic state of matter called Bose-Einstein condensates that I don't understand at all, but my collaborators did, I hope. Okay. And so what is it? We've got a Laplacian for a complex valued wave function. We've got a potential. We've got the wave function here again. This is the parameter that we're going to vary that comes from sort of a time harmonic ansatz, right? So you plug in an ansatz in time, and then this is the stationary equation that emerges. And then this is the nonlinearity. This is sort of the self-interaction that somehow in these Bose-Einstein condensates, what they tell me is that sort of all the particles have the same wave function, and that sounds kind of magical, and so they all interact with each other in this way. Okay, and so what are the symmetries of the problem? Let's get to the interesting question. So the first symmetry is complex phase shifts, right? So this U is now complex valued. And it turns out that if you fix a given theta and you multiply this wave function by e to the I theta, then e to the I theta just pops out of this, it pops out of this, it pops out of this, and it pops out of this, right? So you just get e to the I theta of the original equation. So if you started off with the solution, this is also a solution. So somehow you take the values in the complex plane at every point, you just shift them all by the same angle, and then you still have a solution. What can we do about this? Well, we need, in our deflation operator, to look at something that's invariant under this operation, and it doesn't take a genius, to figure out that what we should look at is the thing that's invariant under complex phase shifts, the norm, right? That's the only thing that's invariant. Okay, so here's such an invariant deflation operator, fine. There's another symmetry group, which is spatial symmetry. So we were solving this in a ball, right? And you can rotate this in 3 dimensions, and it's still the same, right? All the boundary conditions and the forcing and whatever else are all rotationally symmetric. And so that means that you can, if I give you a solution U, and of course this won't be rotationally symmetric in general, and I rotate it, then I also have a solution. Okay? And so what can you do with this? This one is harder, but it's the same principle. You need to look at something that's invariant under all spatial rotations. And so it's this sort of bar operation, which maybe has a more formal name in other contexts. But what it does is, at a given value of the coordinates, what you do is you look at the spherical shell, and you average the original function over that spherical shell. And then that averaged function is rotationally invariant. And so you combine these two, and then you get solutions like this, which are very pretty. So what are we looking at here? This is the magnitude of this complex valued wave function. So this is sort of trying to say in space where it should live. And it can adopt lots and lots of different configurations. It's really, really beautiful. And here I've just drawn 2 isosurfaces just to sort of get a sense of where it is. Of course, it's a complicated function in 3 dimensions. So a whole bunch of different solutions, all different solutions of the same PDE, right? It's very beautiful, I think. And I think that, physicists, maybe chemists, have just much better names than we do, like, vortex ring cages, right? What did you work on today? I worked on a vortex ring cage. Okay, and then the last mathematical extension I want to mention is problems to inequality constraints, because I think this is of relevance to you, because maybe you only want to look for solutions locally within some radius of the solution you already have. Okay, and so problems with inequality constraints arise in many, many contexts. So in my continuum contexts, I would say, for example, I got started in such problems. These are variational inequalities, if you ever heard of them. But I got started in glaciology, believe it or not, because this is a viscous flow, but the key property is that it cannot penetrate the bedrock, right? So whatever happens to the flow, it cannot penetrate the rock. So this gives you an inequality constraint. And so the resulting formulation is one of these so-called variational inequalities. Here's another such variational inequality. Of course, the first thing you think about when you hug your mother. Here are two continua, A and B, and they are in contact, right? And they cannot penetrate each other. So if you fix the position of one body in contact from the point of view of the other, this guy forms an obstacle that he is deforming around but cannot penetrate, and vice versa. So a very beautiful way to describe such an intimate moment. Okay, but it also arises in many other places, especially in economics and finance, because in most things that are sort of games, the optimality condition is that you as an individual with many, many other players around you cannot do any better by changing your mind. So in a traffic equilibrium, the equilibrium is achieved when no driver can improve their travel time by making a unilateral decision, right? That is an equilibrium of the system. And so because you have this inequality constraint, you can't improve something, then you get a variational inequality. The same thing for markets, like a power market, right? So in a power market, you've got suppliers and consumers and so on, right? And the equilibrium is reached when no participant can unilaterally improve their profit. In order to improve your profit, you have to somehow convince other people to do something else. And so on. They also arise in finance, like holders of American options, but I've never solved them. Okay, and so the good news is that deflation also works for such problems. And it turns out that you can write these problems with inequality constraints, like if you just solve an optimization problem with an inequality constraint, as a semi-smooth problem. And there's this thing called semi-smooth Newton, which I don't have time to discuss. But basically, it works the same. Deflation applies just the same to these problems with inequality constraints, is the gist of it. And so here's an example of a simple example of a constrained optimization problem. And in the optimization community, this is quite famous because it is a pathological counterexample to a conjecture about interior point methods, which is one of the main ways of solving constrained optimization problems. But anyway, it's a quadratic programming problem with some inequality constraints. So the feasible set is sort of this region here. Here is our initial guess. You run semi-smooth Newton. It first finds the saddle point, then it finds this minimum, then it finds that minimum. Great. Okay, and so even though for interior point methods this is pathological, deflation just finds them in this way. You can also do it for PDEs. So if you're interested, for example, in the displacement of a structure, you might be minimizing such a potential energy subject to some boundary conditions, and then you would have a picture like this. But if you also impose walls on the top and bottom that your structure is not allowed to penetrate, then now you have such an inequality constrained optimization problem, and you get this variational inequality. And I won't bore you with the details of what the energy is. And here's what such solutions look like, and you can compute them just the same, in exactly the same way, combining deflation and continuation. So here is the constrained equilibrium. And just for reference, I don't compute this in computing this. I don't compute the unconstrained solution, but just to show you that the constraint is really active, the constraint is really doing something obviously big, right? This is the associated unconstrained solution. And similarly, there's many, many other solutions of this problem, some of them constrained and some of them not constrained. And you can also do this in 3 dimensions where you need sort of sophisticated multigrid preconditioners, many different equilibria, many different ways it can rest against the walls. Okay, and so I'm right on time. So let me conclude that, as you well know, nonlinear problems can have multiple solutions, and that deflation is a useful way of computing them. Thanks very much. Question?
Thank you very much. I'm happy to say I now understand what deflation is.